First of all, let me thank the President and the Chancellor for this opportunity to share my own thoughts related to aspects which are of the complexity in space systems, something on which the experience is from our own space program. Yeah. Okay, I think. The complexity in space engineering really comes because the space system engineering schemes are multidisciplinary, and it brings in several aspects of engineering and sciences together. And the launch vehicle provides a fitting example of the complexity, since its design and control calls for the realization of a near cybernetic system. The launch vehicle used is for spacing the various types of spacecrafts. It could be a communication system, it could be an Earth observation system, it could be a scientific mission, and depending on that, put it in the orbits like geosynchronous orbits, polar orbits, or inclined orbits or equatorial orbits. So these are the mission objectives with which the launch vehicle is used for placing a variety of satellites. Now, the complexity of such a system lies in the fact that the system comprises of a number of interacting subsystems, components, and their functions. And this number is very large. Interactions involved are nonlinear, and interactions to interact and can exhibit a range of behavior, often at the edge of instability. So I go to see how such a launch vehicle, and this is an experience again from India's space program, a launch vehicle, what we call as the Polar Satellite Launch Vehicle, how it is got readied, what is the flight sequence of such a launch vehicle, and what are the kind of characteristics that are involved in the flight sequence is what we are trying to show here. The pre-launch checkout is the first of the operations that we carry this out, where hundreds of onboard system parameters are checked and cleared within times of the order of several minutes. And then we come to the next, which is the blast off from the launch pad. And here, of course, the critical issues at the liftoff are the high mechanical, thermal, and acoustic loads generated by the hot jets of the thrust system. The thrust is used for overcoming the gravity in the initial stage, and the vehicle slowly raises. The interaction at this particular point is, of course, an exercise in complexity again, are to deal with ground winds, the problems of thrust misalignments, and the control forces. They have to be managed together to ultimately make sure that the launch vehicle leaves the launch pad without physical contact with the launch tower. The third element, which is what we show here, is the flight into the atmosphere. Here is where the importance of the design of the trajectory comes into picture. The sequence of events are critical here. The shaping of for aerodynamic purposes are validated here, and this has to take cognizance of a variety of optimization processes at each system level. The trajectory design, based on the methods of optimal control of dynamical system, determines where exactly the vehicle will experience high dynamic pressures in the atmosphere. So it's a question of optimizing the position and the velocity to ensure that it goes through smoothly to the areas of what we call as a maximum dynamic pressure, a region which is related to the atmospheric density and the velocity. And here, this is what trajectory optimization is one good example. The next stage, of course, is again continuation into the atmosphere from the transonic, from the subsonic to the transonic regions, and then to the supersonic region. And that is what we show here. It's a continuation of this particular flight. And then we get into the questions of control, guidance, and navigation. This is really, I mentioned about this, it's a near cybernetic system. This is the real brain of the vehicle. The guidance system controls the translational motion of the vehicle, whereas the digital autopilot controls the rotational motion of the launch vehicle. The navigation brings both these together, both the rotational and the translational states of the vehicle, the management of the stage ignition involving shutdown and switching off of the control, separation of the stages, and these are multi-stage vehicles simply because that you want to make sure that you have an optimality with regard to the payload that it can be realized. So you need to have these stage switch off and switch on and separations, followed by ignition of the upper stage and smooth transfer of the control. This is most critical. And this is not only related to the vehicle's characteristics, but it also depends on the atmospheric conditions. And this therefore requires a complex sequence of events based on real-time detection of critical events and corresponding decision making. The next, of course, is the way in which this spent step on. So several stages, once they have lived their usefulness, they are jettisoned according to the predetermined sequence, which is with onboard computers, calculations, and corrections, which are done online. And this spent type round, of course, one of the important thing is most of them come out at the sensible portion of the atmosphere, and they are influenced, therefore, by the nonlinear aerodynamic interactions between the separating bodies. So this is another critical aspect of the whole thing. And then finally, you have the desired orbital parameters into which the system is injected. And of course, once this is done, the propulsive stage is cut off, the satellite is separated, inserted into the orbit for further orbital operation. The aim here is to make sure to inject precisely into the required orbit, minimizing the engineering dispersions. And so these dispersions which come out of the various engineering parameters that control the flight of the vehicle is one of the critical aspects of simulation, which we will see in the next thing. So to summarize this particular set of events, it's an event which lasts for about 20 to 22 minutes in the case of the PSLV, India's launch vehicle. It goes through several regimes, both within the atmosphere and outside the atmosphere. It goes through speeds which are subsonic, transonic, supersonic, and hypersonic, and ultimately based on real-time detection of critical events and corresponding decision making. These are the aspects that one see here. Now, one of the important things with respect to this is to simulate this from the criteria of how well the success of this mission can be evaluated. It's here that we try to look at the Monte Carlo part of a simulation that we have carried out. The Monte Carlo simulation becomes applicable in the case of the flight of a vehicle to evaluate the rationale for its success. Because when a highly complex system is comprised of a number of independent disciplinary subsystems, and these subsystems themselves are involved in complex physical processes, and the dynamics of these independent subsystems is dependent on the interactions with the other subsystems of the main process, then the probabilistic outcome of the main system cannot be easily described by a deterministic mathematical model. When the external forces that influence the main system are also random, for example, in the case of the launch vehicle, it is the atmospheric thing, the dynamics of the atmosphere, the environmental processes of the winds and so on, then the system performance is nearly impossible to be described by a deterministic mathematical model, but it becomes stochastic. So this is where we carry out a mathematical model, and what we are trying to show here in this block diagram is the set of parameters on the right side whose dispersions and whose values are a priori determined by means of engineering experiments, and these are put into the model with respect to the various vehicle parameters, and these kind of variations are done on the dispersions with permutation combination of the multiple parameters which are on the right side, and then try to look at whether it comes within certain levels of stability of the statistical mean as well as the statistical dispersion. Sometimes it takes more than 1,000 to 2,000 simulations before you can get that kind of a convergence on the statistical stability. So that is where, and once that is done, at least you are sure reasonably well that the system is capable of going through the various stages of the flight which we saw in the last case. So Monte Carlo simulation, where the deterministic mathematical models are not able to do, is an important aspect of this, again, a manifestation of the complexity of a flight vehicle. I show here a very interesting slide, and this slide is the outcome of a flight which we did in the early part of our development of a launch vehicle. What we had here in this particular flight was that we had an anomaly. Now this is what we call as an advanced augmented satellite launch vehicle. It has two strap-on to augment the thrust besides the core. It's an all-solid system in terms of propellant. And what had happened in this, and this is also designed purposely with a certain level of aerodynamic instability, mainly to make sure that there are quick responses to the control elements that go into it. Here was an anomaly which started in a small sub-element of the propulsion system. It failed to deliver the expected thrust to control the deviations of the flight in the actual flight. Soon this propagated into the control systems of the vehicle. Then aerodynamic effects, which was because of the atmosphere, accentuated the flight of the vehicle and the problems of the vehicle. It built up itself in the form of an increase in the yaw. And the yaw means essentially you are trying to get the build-up. In the case of yaw means it is ultimately, it is also increases the angle of attack. That is, one is very familiar with the angle of attack when an aircraft makes a nosedive. Structural effects are very severe. So similarly, it went through an angle of attack which was increased in the region, and this happened in the region of the maximum dynamic pressure. I've said about trajectory optimization to ensure that you minimize the impact of a region of the atmosphere for a particular vehicle with respect to how it will respond to the disturbances in that region. It so happened in this design, it was not that well addressed. So ultimately, this increased the structural loads on the vehicle, and which essentially means in this case, the bending moments on the vehicle, and ultimately resulting in a breakup of this vehicle. And all this happened in a matter of 3 to 4 seconds. And you can see the propagation of the anomaly quickly build up in terms of the disturbances, the system failing at a particular point, all in 3 months. So here is a small cause and a big effect. That's what I would like to convey in this particular slide. How does the future looks like in the case of these kind of a thing? Now, if one looks at the futuristic tense, there are new frontiers of space, science and technology. One of the important things is with respect to the low-cost access to the space, interplanetary and deep space exploration, resource utilization, habitat, human habitat, and so on and so forth, and even possibly of defending the planet Earth from disaster of any possible major impact from near-Earth asteroids. So here, there are several new challenges that are come in the space mission complexity. One, of course, is the ability to go to hypersonic velocities, and here there is an intense work on the hypersonic flow research, where really the vehicle control and guidance have to come under severe aerothermal environment, and this itself is a complex problem in terms of the hypersonic flight of a launch vehicle in the atmosphere. Supersonic combustion is another area. The supersonic combustion is there now. There is a lot of interest simply because an air-breathing concept for this kind of vehicle, where you take the atmospheric oxygen instead of using an oxidizer in the vehicle as a propellant, considerably reduces the takeoff weight and increases the payload mass with respect to the takeoff weight. And this is a very important concept that is being developed, but there are problems of computational fluid dynamics, material systems, hybrid systems of propulsion and structure, and so on and so forth. So there is a very challenging and interesting problem in complexity that comes in the supersonic combustion research. And of course, when the man-in-loop systems and with long-term space travel and habitation is involved, the complexity extends further to include astrobiological and environmental factors. Just to summarize, I would like to say something on the way we look at the space flight and the engineering and the complexity. It is tempting to compare the complexity of space engineering, epitomized by the design and launch of a near cybernetic but will-free launch vehicle, space vehicle carrying a satellite, with that of biology, epitomized by the living organism evolved through adaptive responses to selective natural pressures over some 3 billion years, such as a willful human being. Indeed, both are highly complex, though in a qualitatively different sense and context. Both possess complex hardware and software, but biology has the aware solution in addition, and the information is stored in inheritable genes. But really, one should resist the temptation to compare these two any further. Instead, it would rather be reasonable and fruitful though a somewhat distant possibility, namely that biology may and indeed will get incorporated deeply into the complex space engineering programs of future. A remarkably serious example of it could be the Dyson tree, as proposed by Freeman Dyson, developed through a nanobiogenetic engineering that could support a natural habitat for living organisms, including humans, in a spaceship or an asteroid. I think the humankind is always space-bound, simply because of the fact that we habitate one of the most complex systems that we are aware of, the Mother Earth. Thank you very much.